Hello everyone, a very good evening to you all. Welcome to SPSVERSITY. I am here, your chemistry educator. So I'm going to take up the third part of aldehydes and ketones and the ending topic of that's called as carboxylic acid. So please keep watching SPSVERSITY, like our videos and subscribe so that we can deliver good content for you. And if in case of any suggestions, please put it in the chat box. So during the session also you are very free to express your answers or queries, and you can put it in the live chat section. So today I'm proceeding with the next topic, that's a carboxylic acid. In the previous sessions we saw aldehydes and ketones. Just a recap: in case of aldehydes, ketones and the carboxylic acid, what we had which is common was a carbonyl group, that's C double bond O, where carbon is sp2 hybridized. And the same thing follows here also. In case of carboxylic acid, the carbon is sp2 hybridized, and then when you name the carboxylic acid you end it with oic acid. This is a suffix which is given to the carboxylic acids, and if you have two, then you name it as dioic acid, trioic acid, like that. And also this is a high priority functional group. If you have aldehyde or ketone or alcohol or amine, you are going to give the priority to the carboxylic acid group, and it is taken as suffix. So the common names which is found in the red rand, that's formic acid, which is called as methanoic acid. Depending on the number of carbon atoms you are going to name it. Acetic acid, it was found in the vinegar, so it is called as acetic acid. And the IUPAC name is there are two carbon atoms, so it is eth type of bonding, a single ane at the end, oic acid. Propionic acid and butyric acid, which is found in the butter, and valeric acid in the plant root, caproic acid, caprilic acid, capric acid, which have their own names. Okay, so we'll go to the general methods of preparation in case of carboxylic acid. When we speak about the carboxylic acid, we refer to the preparation of monocarboxylic acid. The carboxylic acid is containing one COOH group. So first thing what you can do is, by the oxidation of primary alcohol with acidic K-aminophore or acidic K2Cr2O7. So which is a very strong oxidizing agent. So when you oxidize, you have RCH2OH like this, and when you treat it with K-aminophore, the acidic K-aminophore or the acidic dichromate, what you're going to do over here is replace these two hydrogens and put a double bond over here. That is going to give you RC, oh, you have removed this, H double bond, RCHO. This is nothing but an aldehyde, which on further oxidation will give you this is where the oxygen gets added, so you get RC double bond OH. And oxidation of aldehyde, just like here you are using K-aminophore in the presence of an acid, so alcohols directly get converted to carboxylic acid. And if you have to start from aldehydes, then you can oxidize them using the mild oxidizing agent like the tolerance reagent, which is ammonical silver nitrate. Tolerance reagent is ammonical silver nitrate. You are going to use the ammonical silver nitrate, where the silver is going to carry a charge of +1. During the reaction, if you have RCHO, that's aldehyde, that gets converted to RCOOH, say carboxylic acid, and the Ag plus that gets reduced to Ag, which forms silver mirror in the test tube in which you are going to carry out this test. So you take the aldehyde, you treat it with the ammonical silver nitrate, and you boil it in a boiling water bath, and you're going to get the carboxylic acid, and the silver is going to get precipitated. This is the second method of preparation of carboxylic acid. We'll move to the other preparations. By the oxidation of alkenes, You take alkene and you are going to take the KMnO4 in the basic medium, and then you hydrolyze the product so that you are going to get, this will break, and both the sides you are going to get the carboxylic acid, RCOH and RCOH. So if you have something like CH3, CH2, CH, CH3, if you are going to do the oxidation of this one, there is a rule called as Popov rule, according to which the yeah sorry sorry when you do the carboxylic when you do the oxidation of this will break in such a way that you're going to get, this will break and you're going to get CH3, CH2, this part gets converted to COH, and plus this side it gets converted to HCOH. The number of carbon atoms will be retained on either side, so you get a propanoic acid and you get methanoic acid. And then by carboxylation of Grignard reagent, so you take alkyl halide, that is Rx, and you are going to treat it with Mg. So Mg gets introduced in between so that you get RMgX. When this RMgX is treated with carbon dioxide, the carbon dioxide will go inside. That's going to, okay, so otherwise you can say R is negative, Mgx is positive, partially positive, this is partially negative, and you have C double bond O, C double bond O like this, which is linear actually. This will go and attack here, this will shift here, which is going to take R Mgx. So because of this you are going to get R COO Mgx. When you hydrolyze it, the acid hydrolysis of this is going to give you RCOOH plus Mg X was already there, you are going to get RMgOHX. This is how you get the Grignard reagent, the carboxylic acid from the Grignard reagent. Then any acid derivatives, if you take, for example, it can be acyl halide, you are hydrolyzing it, or it can be anhydride, or it can be ester, or it can be amide. All of them are going to give you the carboxylic acids on acid hydrolysis. And then the cyanide hydrolysis. So if you have alkyl cyanide, or this is called as alkane nitrile, when it is hydrolyzed, so R C triple bond N is what you have. When you acid hydrolyze it, you are going to get RCOOH. This is one of the other reaction. And then oxidation of alkyl benzene. The CH3 group which you have over here, in the presence of strong oxidizing agent, this gets converted to the corresponding carboxylic acid. And if you have any group like this completely gets converted to carboxylic acid, COH. But here you have C like this. So this doesn't get converted to corresponding carboxylic acid. So though there is no reaction in this case. And then we are going to see the chemical properties of carboxylic acid, how these carboxylic acid are going to react. And in this particular reaction, we speak about the acidity of the carboxylic acid. Whenever you say acidity, this is because of the, if you write the compound like this, R C double bond O H, then you see here, this is the non-equivalent structures and these are the equivalent structures. If you see the carboxylate ion, this will dissociate into RCOO minus and plus H plus. If you take the carboxylate, that's RCOO minus, then this is in resonance, because of which it is considered as more acidic compared to alcohol. So acidity is relative case with which it loses a proton, and you are going to get the anion which is called as carboxylate ion. Its strength depends on the difference in the stability of the acid and its ion. So if you take the stability, which is more stable, depending on that the acidity is determined. And if you have any electron withdrawing groups, so the more polar is this OH group, if you see this RCOOH, more is the polarity of this OH group, more acidic it is. So if the polarity has to increase over here, there should be some electron withdrawing group. So if you have RCOOH and if there is some electron withdrawing group attached here, then that is going to pull out the electrons, because of which this becomes more polar. That OH bond becomes more polar. When it is more polar, it can be easily broken. That means it will give H plus easily, and this becomes more acidic. Instead, if you have any electron releasing group, so if you have a methyl group attached to this, so methyl is the alkyl groups are electron donating groups, because of which the OH bond becomes less polar. So H plus cannot be easily given, so this is less acidic. So when you generally speak about the acidic strength of the carboxylic acid, you have to say that any electron withdrawing groups, they increase the acidity by making OH bond more polar. And if you have electron donating groups, then the OH bond is going to become less polar and it is called as less acidic. So whenever you see carboxylic acid, we have different groups of, I mean, the OH here, you can break this bond if this particular bond is broken. And what happens if you break this bond? So you have to see how this bond breakage takes place. First, we are going to see the reactions due to the cleavage of OH bond. This bond is broken. Now, the first one is the reaction with the metals. When the carboxylic acid reacts with the metal, say two molecules of carboxylic acid react with the sodium, and you get two ROCNA, that's a sodium salt of carboxylic acid, and the hydrogen gas is liberated. Here you see the OH bond, the bond between OH and O and H is going to break, and the hydrogen is given out. And the reaction with calcium oxide, if you treat this with calcium oxide or the calcium carbonate, again say the reaction follows like this, RCOOH, and you are going to treat it with calcium oxide. Now this bond is going to break. There was one H which is getting replaced by calcium, which is a divalent. So you get RCOO twice, that's a charge on calcium, Ca, plus you get H2O, so you put 2 over here. This is again OH bond breakage. And the reaction with bicarbonates and the carbonates, instead of calcium oxide, if you take the calcium carbonate and RCOH, that is treated with sodium bicarbonate, and this H gets replaced by either calcium or sodium. If it is a bicarbonate or the carbonate, you are going to get the carbon dioxide along with water as the byproducts. Okay, this is one more reaction. And in this reactions, all the three reactions, we saw the bond breakage, which is between O and H. Now we see the bond breaking. That's if you take RCOOH, this bond will be broken. So the first reaction, which is very important, is esterification. Acid, carboxylic acid, and the alcohol in the presence of acid catalyst, they combine to give an ester which is having the fruity smell. Okay, so this is how the reaction proceeds. So you have a carboxylic acid of the form RCOH, and you have an alcohol of the form ROH. When these combine, you eliminate one water molecule like this, and what is that? You are going to get RC double bond O, and here there is O and R, plus you get H2O. This is how the reaction proceeds, and this is an ester. And also, if you treat the carboxylic acid in the presence of phosphorus halide, you are going to get corresponding acyl halide. You can even treat it with SOCl2, or you can treat it with the thionyl chloride or the sulfonyl chloride. In both the cases, you are going to get the SO2 gas along, and I mean SO2 and SO3 gas along with the formation of HCl, and OH gets replaced by the group which is Cl. And you have two molecules of carboxylic acid. If you are going to treat two molecules, say RCOOH plus RCOOH, if you are going to heat this in the presence of phosphorus pentoxide, then this is what you expect. One water molecule goes away, and you are going to get R, C double bond O, and you have one oxygen over here, and C double bond O, and alkyl group. So this is called as anhydride. So you are going to get acid anhydride because one water molecule is removed. That's why it is anhydride by the combination of two acid molecules. Then we have soda lime decarboxylation. So it is a one. If you start with 2 carbon atoms in the parent carboxylic acid, you end up with an alkane with one less carbon atom. So how does it proceed? You are going to treat RCOOH in the presence of soda lime, which is a mixture of sodium hydroxide and the calcium oxide. And what is that you are going to get? You are going to get this the entire group from here will go. That's a CO2 removal takes place. That's why it is called as decarboxylation. And you are going to get RH at the end. That is a hydrocarbon. Then you have Hunziker reaction, in which the carboxylic acid is treated with silver oxide. And you see the silver gets added in the place of H goes and the silver gets added. When it is treated with bromine in the presence of CCl4, the bromine, the CO2 goes again. Here the CO2 goes, and one of the bromine combines with Ag and the other bromine combines with R. So you get alkyl halide or alkyl bromide at the end of the reaction. So the difference between the soda lime decarboxylation and the Hunziker reaction is, in case of soda lime decarboxylation, you start with the carboxylic acid and at the end you are going to get the corresponding hydrocarbon, whereas in case of Hunziker reaction, you start with the carboxylic acid and at the end you are going to get the alkyl halide. So how do these carboxylic acids are going to react with the organometallic compound like the Grignard reagent now? So if you treat RC double bond OH with CH3 MgBr, what is the reaction you are expecting? So this CH3, which is negative, this goes and attacks here, so the movement of this one takes place. You get RCCH3 and this takes MgBr, O MgBr plus OH, and then after this the CH3, whatever you have, can you see this reaction? And after this will rearrange in such a way that the CH3 will go with one hydrogen, so you get CH4 and you get RC, this shifts over here, so you get a double bond here, RCOOMgBr. This is what you're going to get at the end. If you're going to treat it with the lithium, this methyl lithium, then you're going to get the corresponding lithium salt of carboxylic acid, which then reacts with one more molecule, and then on hydrolysis this is going to give the vizinaldiol, which is unstable, which is going to give you which is going to lose a water molecule, and this gives a ketone. This is very important reaction. Once again, this is Hvac-Volat-Zelinsky reaction, where you are going to take a carboxylic acid with alpha hydrogen and you are going to treat it with red phosphorus and the bromine. For example, if you take CH3 C double bond O OH, you are going to treat it with the presence of Cl2 over red phosphorus, one of the hydrogen. This is the functional group now. The carbon which is immediately attached to it is called as alpha carbon. The hydrogen attached to it is called as alpha hydrogen. So one of the Cl from here will go with H. So you get HCl as one of the product, and this particular H here gets replaced by Cl. So you get Cl, CH2, COH. This may react with one more molecule until all the alpha hydrogens get replaced. This is called as alpha bromo acid. In this particular case, here it is called as chloroethanoic acid. 2-chloroethanoic acid. Why this reaction is very important? Because this particular reaction, after the alpha halogenation, the product which you are going to get, that can be used as the primary source of for the synthesis of varieties of organic compound. Say you take the alpha halo acid, which is going to react with the amine to give the alpha amino acid, then it is treated with the base to get the hydroxy acid, then it is treated with the alcoholic KOH, then you get alpha beta unsaturated acid, which is then treated with cyanide, and you get a cyanide compound, and which on hydrolysis is going to give you the dioic acid, because of which it finds a lot of application. That's why this particular reaction is very important when you take into consideration of the factory manufacturing processes. So this is what happens when you treat a dicarboxylic acid. if you are watching the videos, please support us, and if I'm going too fast or anything, you can always um, let me know. I'm just checking. Okay. So your exams are nearing, and I think you are preparing very well for your exams. Yeah. So here we go. Yeah. If you take the dicarboxylic acid, for example, the succinic acid, where you have, I'll write it this way: CH2CH2, C double bond O OH, and then C double bond O OH. This is a succinic acid, which is a dioic acid where you have two carboxylic group attached to the same compound. A water molecule gets eliminated from here, and what is that you are going to get? CH2, CH2, C double bond O, O, C double bond O. This is called as anhydride. When two carboxylic acid molecules combine, or if a dioic acid undergoes dehydration, then you are going to get the anhydride. The same thing happens in the glutamic acid also, which you are going to get the glutamic anhydride at the end. Then the reaction with the tolerance reagent. Formic acid is a special case, which acts as a strong reducing agent. If you take the tolerance reagent, uh, the carboxylic acid gets converted into carbon dioxide and water, whereas silver oxide get reduced to silver. And this is also going to react with the Fehling solution, where it is going to turn the blue color of that to red precipitate. And also this is going to react with the mercury chloride, where it is going to reduce the mercury from state 2 to state 1, which is going to give you the white precipitate. Because of this, you can always say that the formic acid can behave as a good reducing agent, where it can reduce the tolerance reagent, it can reduce the Fehling solution, it can also reduce the mercury chloride. So that's all about the carboxylic acids. Now we move on to the MCQ section. So I want to put your answers in the comment section. Aldehyde is the first oxidation product of what? The options are primary alcohol, secondary alcohol, tertiary alcohol, and dihydric alcohol. What do you think is the right answer? So you should get aldehyde is a primary first oxidation product of what? So you get aldehyde after oxidation. That means the reverse reaction which you're expecting is a reduction. So reduction is remove addition of hydrogen, whereas oxidation is either addition of oxygen or the removal of hydrogen. So you can always say primary alcohol, secondary alcohol, tertiary alcohol, and dihydric. If you add, this is RCHO. If you add hydrogen to both this one and this one, what is that you are going to get? R, CH, H. This double bond gets converted to single bond. So you are going to get the primary alcohol. If you take the secondary alcohol, you are going to get the if you take the secondary alcohol, or if you take the secondary alcohol, you are going to get the ketone. If you take the tertiary alcohol, you're going to get the alkene. So the correct answer would be the primary alcohol is produced from the aldehyde is produced from the oxidation of primary alcohol. We'll go to the next question then. What will be the order of reactivity? So what do you think is the right answer? What will be the order of reactivity of the following carbonyl compounds with the Grignard reagent? So we start, so Grignard reagent is RMgX. The carbonyl compound is C double bond O. And it is RMgX, which is negative, that's going to attack the electrophilic center over here, which is carbon. This is a positively charged and this is negative, the partial positive and the negative. Now if R has to come and attack C, this should be more electropositive. If it has to be more positively charged, then there shouldn't be more alkyl groups. If you have more number of alkyl groups, more is the number of alkyl groups, what is going to happen? If there are more number of alkyl groups, then the electron density on carbonyl carbon is going to increase. When it increases, it is less reactive towards the nucleophilic substitution for R minus attack. So you have to select the order. All of them, the order which they have provided is a decreasing order. So less is the number of less is the alkyl group, increase in the order is seen. So if you go here, there is no alkyl group, here there is one alkyl group, here there are two alkyl groups, here there are more number of alkyl group, because of which the reactivities, the formaldehyde reacts faster than the acetaldehyde, followed by the next compounds. So the correct answer would be option 4. Methyl ethyl ketone can be reduced to N-butane by. What do you think the answer is? You can always put your answers in the comment section. Okay. Methyl ethyl ketone. What do you mean by that? It is a ketone. On one side you have methyl group, the other side you have ethyl group. It can be reduced to N-butane. N-butane is when this C double bond O gets converted to CH2, because you don't have any other option here to convert. The reduction, you have to do the reduction. We'll go according to the options. If you go ahead with the option A, that is Meerwin-Pontroff reduction, it is the one where the ketone is reduced to get, instead of this one you get alcohol. The hydrogen adds on both sides of the double bond, so you get alcohol. And if you go with the second one, Wolff-Kishner reduction, that uses hydrazine. You use hydrazine. For example, if you take CH3, CH2, I'll put it as C2H5, and then C double bond O, and then CH3, then plus NH2, NH2, then one water molecule gets eliminated from here, then you are going to get C2H5, C double bond N NH2, which is called as hydrazone, and then after this you are going to, I said, hydrolyze this, so that you are going to get C2H5, C in the place of double bond in you get HH and CH3. So this is a way you are going to convert the methyl ethyl ketone into N-butane. So this would be the right answer. But if you take the C, option C, MgHg, then that's magnesium mercury amalgam, then you are going to get the methyl ethyl ketone. This is CH3, CH2, C double bond O and CH3, because of which two molecules of them undergo reduction, and they are going to combine in such a way that CH3, CH2, this gets converted to alcohol group, and the CH3 goes down, and this is going to combine with one more molecule of the same kind to give CH3, and you are going to get CH2, CH3, which is going to give you a pinacol. This is called as pinacol. So the correct answer would be option B over here. The next question which we have, an organic compound with the molecular formula C5H10O yields phenyl hydrazone and gives a negative response for the iodoform test and the tolerance reagent. It produces N-pentane. On reduction, the compound could be. What do you think the answer is? So most of the things they have given over here. So an organic compound X with the molecular formula, they have given you the molecular formula C5H10O. Sorry, I'll rewrite it again. So the molecular formula of the compound is given. That's C5H10O. This answers phenylhydrazine test. The one which can answer the phenylhydrazine test is aldehyde or ketone, and now gives a negative response for tolerance test. The tolerance test is answered by only aldehyde, and tolerance reagent cannot oxidize the ketone. So it could be a ketone, and you are doing the iodoform test. This iodoform test is answered by the methyl ketones. That means a ketone which is attached, or C double bond O, which is attached to the CH3 group. Now if you take the pentanol, it can't be the answer because this is not going to answer the tolerance test. Pentane 2-one is C double bond O, C. It could be the answer because it is a methyl ketone, so this is going to answer the iodoform test. It doesn't answer the tolerance reagent, and it is going to answer the phenylhydrazine test. So this could be one of the answer. We'll check with the other answers too. Pentane 3-ol, that's C2H5, C double bond O, C2H5. There is no methyl group, so it doesn't answer the iodoform test. Okay, so amyl alcohol, this is definitely not an answer. So the correct answer will be option B, that's pentane 2-ol. And they have also given it produces N-pentanone reduction. Both pentane-one and pentane 2-one and pentane 3-one, that can give the on reduction, they can give N-pentane, but the correct answer would be option B. Ethyl reaction involves the preparation of benzaldehyde from. The answers are benzoyl chloride, ethyl benzene, methyl benzene, and sodium benzoate. What do you think the answer is? What do you think the right answer is? So whenever you say ethyl reaction, you are going to convert this group, that's the toluene methyl benzene, to benzaldehyde, and this is done in the presence of Cr go to Cl2, chromyl chloride. So the correct answer would be methyl benzene, or it is also called as toluene. The formation of aldehyde from alkyl cyanide is related with the name. So we'll go according to the option. The first one, Stephan reaction, is the one where you're going to treat RCN. You're going to reduce it in the presence of SnCl2 over HCl, and this gets converted to imine, which on hydrolysis is going to give you aldehyde. And if you're going to take Rosenmund, this involves the conversion of RCOCl in the presence of palladium over barium sulfate, and you're going to get RCHO. And the third one, Wood's reaction, this is the one where you're going to take RX, two molecules of RX, and you're going to treat it in the presence of sodium over dry ether, and you are going to get RR. And the next one is HVZ reaction. In this particular reaction, what you are going to do is you are going to take RCOH, and you are going to treat it with the presence of any halogen, say X2 in the presence of red phosphorus, and then you are going to get X substituted compound, alpha halo acid. So the correct answer where you are going to convert the cyanide to aldehyde is the first one, which is called as Stephan reaction. The end product of this is, they have given you the acetic acid. You have to treat it with calcium carbonate so that you are going to get A, which is then heated to get B, and then it is treated with hydroxylamine to get C. So what do you think it is? Yeah, we'll go ahead with this. So when CH3COOH is treated with calcium carbonate, the carbon dioxide gets evolved and you get water from here, and this hydrogen will go in that place, you get substituted with Ca. Since Ca is divalent, you need two molecules, so that you are going to get CH3COO twice Ca, calcium salt of acetic acid or calcium acetate, which is when heated, this is going to give you the calcium carbonate. If you remove the calcium carbonate, what you are left with? You have CH3COO, CH3COO, minus, minus, and Ca2 plus. You're taking one calcium, COO, and one more O. And you are left with these molecules combined, and you get CH3, C double bond O, CH3, which is acetone. When this acetone is treated with NH2OH, from here oxygen will go, from here hydrogen will go, and you are going to get CH3, C double bond NOH, CH3. This is nothing but this is acetoxime, or this is also called as ketoxime. So the correct answer would be option B. You don't get acetaldehyde, you don't get formaldehyde oxime, you don't get methyl cyanide. Instead, you get the ketoxime. That would be the right answer. So you have the Rosenmund reduction, that's acyl halide. When it is reduced in the presence of palladium or barium sulfate, you are going to get aldehyde plus HCl. What is the role of barium sulfate in this particular reaction? What do you think it is? Yeah, we'll go ahead with this since When this is reduced, RCO, in the place of Cl, what you are going to get is H. And the palladium, which acts as a reducing agent. It's a strong reducing agent which can further reduce this aldehyde to alcohol. If you don't want this to happen, then this reducing agent, that's palladium, is poisoned. What do you mean by poisoned? With barium sulfate. What do you mean by poisoned? You are going to reduce the catalytic activity. The catalyst shouldn't act so much so that you get the next product, which is alcohol, which you do not want. If you want the reactions to stop at aldehyde, then you are going to treat it with palladium or barium sulfate. So that is poisoned with barium sulfate. When it is poisoned with the barium sulfate, it is going to deactivate palladium so that it doesn't act very much. So the correct answer would be option C. We have the next question. Compound A, when treated with ethyl magnesium iodide in dry ether, forms an addition compound which on hydrolysis forms compound B. The compound on oxidation produces 3-pentanone. Hence the compound A and B are. Okay, so you take the compound A, which is then treated with ethyl magnesium iodide, iodide, C2H5MgI, and in dry ether, this is going to give you an addition product which on hydrolysis gives you B. This B on oxidation is going to give you 3-pentanone. You have to determine what is A and what is B. So we'll write the structure of 3-pentanone first. CH3, CH2, C double bond O, CH2, CH3. This is 3-pentanone. Say you before oxidation, if you take the reverse reaction, it should be a reduction, right? If you go in the reverse order, this should be reduction. When it is reduced, you are going to get an alcohol. Since this contains 5 carbon atoms, even the alcohol should contain 5 carbon atoms. So that could be CH3, CH2, COH in this place, and CH2, CH3. You add hydrogen across this double bond, and this is nothing but B. So the B is an alcohol which is 3-pentanone. So you have options A, B and D as B, which is the right answer. Now if you take C2H5MgI, you have added to the compound this. You have 5 carbon atoms over here. There are 2 carbon atoms over here. So 5 carbon minus 2 carbon atoms. Put together 5 carbons minus 2 carbons. They should give you 3 carbons. So there should be the presence of 3 carbon atoms over here. That means it could be propanol. We'll anyhow write this. Propanol is CH3, CH2, C double bond OH. When you treat it with MgI, this will go here and this will go here, and you get this one. So that you are going to get CH3, CH2, C OMgI and CH C2H5, which on this is the addition product, and which on hydrolysis is going to give you the alcohol. So the correct answer would be option A. Which of the following compounds cannot form an optically active cyanohydrin on reaction with HCN? So what do you mean by optically active? What is the first condition? You should have a chiral carbon atom which should be attached to, what do you mean by chiral carbon atom? 4 different groups. So if you take into consideration of this, CH3, CHO, when this is treated with hydrogen cyanide, Cn minus is a nucleophile there, this shifts here, and after hydrolysis, what is that you are going to get? CH3, C and OH, H and Cn. So this is attached to 4 different groups. This can give you the optically active compound. Benzaldehyde is C6H5, CHO. When you treat it with Cn minus, the Cn minus will attack here and this will go up, so that you are going to get C6H5, COH, and Cn here and H here, because this is also optically active. Then the next one, 2-pentanone, that's CH3, C double bond O, pentanone, C3H7, totally 5 carbon atoms should be there. When you treat it with Cn minus, the Cn will go and attack here, this will go here. As a result, you are going to get CH3, C, C3H7, and OH and a H. Again, this carbon is attached to 4 different groups. But if you take the last one, 3-pentanone, that is C2H5, C double bond O, C2H5, and when it's treated with the Cn minus, this Cn minus will go and attack here, this will shift here, because of which you are going to get C2H5, COH, H, and C2H5. Since there are 2 carbon atoms, the similar groups on attached to the carbon atom, so this is considered as optically inactive. So this should be the right answer. With the help of following Grignard reagent, which carboxylic acid is formed? CH2 double bond CH, CH2Br. When you treat it with magnesium in the presence of ether, this will go and sit in between. So you get CH2 double bond CH2, CH2MgBr. When it is treated with carbon dioxide, this is the negative part which will come and attack over here. So this will shift here. This will go and take up this one, MgBr. And you are going to get CH2 double bond CH, CH2, C double bond OMgBr. Which on hydrolysis, this will go and you are going to get CH2 double bond CH, CH2, COOH, and MgOH, Br. So the correct answer would be CH2 double bond CH, CH2, COH. So the correct answer would be this one. The product obtained in this reaction is, so this is nothing but the HVZ reaction. If it is a HVZ reaction, what you are going to do is CH3, CH2, there are 2 hydrogens attached to the carboxylic acid group, that's alpha hydrogens. When it is treated with Cl2 or phosphorus, both the alpha hydrogens get converted to the chlorine atoms. They get replaced by the chlorine atoms. So you get CH3C, Cl2COH, which could be option C. Option C is the right answer. Then the next question which we have here is, which can reduce the carboxylic acid to alcohol. So generally the strongest reducing agent can be lithium aluminum hydride, which is not given over here. It cannot be sodium or ethanol. It cannot be hydrogen, or because it can only reduce the double bonds. If you take sodium borohydride, that's NaBH4, this can reduce aldehydes and ketones, but not the carboxylic acid. So the one which is remaining, which can reduce this, is BH3 over tetrahydrofuran in the presence of acid catalyst. When propionic acid is treated with aqueous NaHCO3, CO2 is liberated and the carbon from CO2 comes from. So how do we do this? So you take NaHCO3, propionic acid, that's the carboxylic acid with the 3 carbon atoms. When it is treated with NaHCO3, so this particular H gets replaced by Na. So you get CH3, CH2, COONA, and this one, 2 hydrogens combine and you get CO2. This carbon comes from HCO3. That's not the methyl group, not the carboxylic acid, not the methylene, but it comes from bicarbonate group. That could be the right answer. Which of the following is correct for the benzoic acid? What do you think is the right one? First, you should know what exactly is the nature of COOH group in the benzoic acid. So it's like This is benzoic acid. In this benzoic acid, the COH which is attached to the the benzene, it is a deactivating group. So if you write the resonance structure, this is going to pull the electrons, so this shifting takes place, because of which here there is a positive charge and here it is double bond C O minus OH. And when you write the structure, resonance structures of this, so this will shift over here and you're going to get a positive charge here. This is a ring deactivating group. So you get ortho and para positions are electron deficient now because they have a positive charge. Now nitration and the bromination, if you take the nitration, you are going to add NO2, and if it is a bromination, you are going to add Br3 plus, which are electrophilic substitution. Electrophilic substitution cannot happen at ortho and the para position, but it can happen at the meta position, because compared to ortho and para, meta doesn't have any positive charge. So the nitration and the bromination should give you the meta product here and here, so this won't be formed. The Friedel-Crafts reaction is electrophilic substitution, which doesn't happen for the benzoic acid. So the reaction with concentrated sulfuric acid, that gives 3-carboxybenzene sulfonic acid. That means once you this is a SO3H which is going to get added to the meta position, and that's why you are going to get the 3 substituted product. That is the only right answer. 3 is nothing but meta position. The acidity of the compounds ROCOH, H2CO3 and all is. We know that carboxylic acid is a better acid because it is going to give you H plus soon, because it is attached to the C double bond O compared to the carbonic acid. So RCOH comes in the first, so that would be this one. But still we go ahead. If you take the phenol, the lone pair of electrons are involved in the resonance, because of which it can give H plus easily. And if you take alcohol, that's ROH, there is no resonance involved, so this is the weakest one. This can the OH is not that polar, because of which it can't give the H plus in easily. So the correct order will be carboxylic acid is a stronger acid compared to carbonic acid, compared to phenol, compared to alcohol. A liquid which is mixed with the ethanol and a drop of concentrated sulfuric acid, the compound with fruity smell is formed. So the liquid was always, it is the ester which is being formed from carboxylic acid and an alcohol in the presence of acid catalyst. So liquid was mixed with ethanol. So one is alcohol. Which is the other one? It should be definitely the carboxylic acid, so that you get the ester after the reaction. So that is the end of the topic aldehyde, ketone and the carboxylic acid. I have explained it up to my best knowledge, and I have given you a couple of MCQ questions as well. So I think you enjoyed the session. If you like the videos, please put a like button and subscribe. Don't forget to subscribe, because your feedback